Okay, so I think we can start. We actually have 2 minutes, but I would like to take this opportunity to introduce our distinguished guests, Dr. Pratanu Ghosh, who is an associate professor of civil and environmental engineering at Cal State Fullerton. His research expertise is primarily focused on sustainability and durability investigation of high performance concrete materials, service life modeling using reliability assessment, health monitoring and quality control and quality assurance of bridge deck design and construction using emerging experimental and numerical technologies. Recently, he has established research collaboration with faculties in Europe for development of robust service life modeling software. In addition, he has developed significant connection with several companies in California and around the nation for donation of materials and equipment for future research. Over the last 9 years, he has actively engaged numerous undergraduate and graduate students with hands-on experience in infrastructure materials research and he has published numerous high-quality journal and conference publications in this area. Besides research, he likes to explore various national parks around the world. So I would like you to welcome our guest, Dr. Pratanu Ghosh. Dr. Ghosh.
Thank you, Janice, for your great introduction. I'm really thrilled to present my research experience throughout here at Cal State Fullerton to all of you. I think it's my real pleasure for the invitation from you and from you and to present my research experience with you all. So with that, I'm going to share my presentation slide. Uh, So I'm going to talk about basically today parts. One is your what kind of high performance concrete material should we choose for enhancing the service life of bridges and pavements throughout the US, and what kind of emerging new non-destructive testing should we follow for better evolution of our nation's infrastructure, especially concrete and concrete pavements. So being said that, we need to think about that what we are talking about concrete infrastructure. So as we know, like 70% of all bridges in the US are made of concrete. That's the federal highway data from 2016. And in 2015, 80.4 million tons of Portland cement was produced in the United States for construction of concrete bridges, pavements, or other infrastructure like the tunnels and dams. So we can imagine concrete is one of the most versatile and most widely used construction not only in the US, all throughout the world. So being said that, we most probably everyone is aware of that concrete is made of aggregate rocks, fine aggregate sand, cement, obviously, and water. And sometimes we need some chemical admixture to enhance the process of the concrete. So I'm going to talk about kind of a little bit more in layman's language. I know some of the part of the presentation are highly technical, but I will touch down and try to make sure that it is more like general. So being said that, what is the biggest problem right now in US concrete infrastructure, especially in concrete bridges and pavements? So we know, uh, other than Southern California, we know most of the parts of the US that we are going through in winter heavy amount of snowstorm or snowfall. So these roadway salts we put basically in the bridges and in the pavements to melt the snow in the winter. But there is a challenge, even though the snow is melting, but sometimes we forget that this salt starts to ingress from the top of the concrete slab and going through the concrete over the time, and then it starts to attack the reinforcement, the rebars with concrete, which is basically susceptible to corrosion. So this rebar corrosion is one of the major challenge which is happening by chloride ion ingress. The chloride salts basically. Generally, you put sodium chloride or potassium chloride on the top of the bridge deck slab or pavement slab to melt the ice. But that salt has a detrimental effect, as we can imagine. So every year we spend at least $90 million for bridge repair replacement, just for bridge repair and some periodic rehabilitation. So we have to think about it. It's becoming a burden on U.S. Federal Highway Administration and federal government. So what is the possible solution we can think about? Obviously, we can think about the original cement that were used, like in last 40 years bridges or 50 years bridges, which generally last the bridge deck slab approximately 30 to 40 years. Not the whole structure I'm talking about, just the bridge deck slab or pavement slab. After 25 to 30 years, every time you need to replace the whole slab and then you need to put the new slab, which is a big expenditure. We can imagine we are putting $1 billion infrastructure, and every 25 30 years we are replacing the whole bridge deck slab. Uh, so instead of that, we can think about how improved materials we can use, like more sustainable as well as durable materials. These days we are all talking about also the sustainability part, because we know that if we use more sustainable materials, then you can reduce the CO2 emission, greenhouse gas emission. Second part we can think about, we need to reduce the diffusion coefficients of chlorides. So what does mean by diffusion coefficient? We know that chloride is diffusing through the concrete from the top of the slab, and then it starts to ingress through the concrete, and after a certain amount of time it starts to attack the rebar, basically the reinforcement within the concrete. So diffusion is the mechanism through which chloride is going through. So if you can reduce, basically delay the diffusion process of chlorides and increase the resistivity. So resistivity is the basically indirect way of measurement of chloride penetration in the concrete. So if we have higher resistivity and lower diffusion, then obviously the concrete will be really good one, and it can delay the diffusion of chloride. So it will take a long time to basically initiate the corrosion. Again, it's a natural process, so there is no way that we can remove the corrosion. All we can do, we can use really good sustainable durable materials, we can use better reinforcement, and then we can predict a better way the service life, so the rehabilitation process will be more smoother. So Federal Highway Administration will coordinate with different Department of Transportation when will be the rehabilitation time, instead of every year some maintenance. So being said that, how bad it could be the corrosion process, we can see some of the pictures. You see how the rebar looks like when it gets really a bad way, it is affected by corrosion. Some of the columns is the all the reinforcement are exposed. After a certain amount of time, it is basically functionally becomes obsolete. That doesn't mean that it will right away fall, the whole structure, or collapse, but it functionally becomes basically problematic. And even it continues with the heavy amount of traffic load. We know some of the times it is the combined effect of corrosion and the traffic load, which happens in Minnesota 10 years ago. There in I-35, one of the bridge collapsed basically due to corrosion. Initially, the problem was there, all the cracking developed, rebar were exposed, and then on top of that, heavy traffic load was going on even on top of the bridges. So being said that, this is one of the major problem in concrete infrastructure. There are other problems out there in concrete. We can imagine there are sulfate attack, acid rains, and then alkali silica reactions. So many problems are there in concrete. Although concrete is most versatile material, but there are heavy challenges involved to deal with concrete. That's why engineers are always updating the research methods to improve the quality of the concrete, because concrete is very cheap. Concrete is easily mold up, so you can easily build any structure with concrete compared to other material like steel or wooden material. So being said that, let's talk about the chloride induced corrosion. As you see the pictures, it is one of the biggest threat to our nation's infrastructure. Being said that, what things can happen when corrosion happens? So one of the things you can imagine, concrete is very weak in tension. Tension means pulling away. If you try to pull away the concrete from the side, then it starts to crack, develops heavily. Whereas if you try to push the concrete, then it is Okay, concrete is very strong in compression if you're pushing. So pushing means compression, pulling away is tension. So concrete is very weak in tension. So due to corrosion, concrete's tensile capacity starts to weaken. So that is one of the major challenge. And we see always that some concrete covers are there. Covers means, some amount of cushions are there before the reinforcement are placed, basically after the cover. So if you have very less cover, then that is also challenge, because if the corrosion happens easily, then the rebar gets exposed, and then obviously the corrosion starts to propagate heavily, and then obviously functional part will be gone. So this is the chloride induced corrosion mechanism. Again, I'll just start to tell how the corrosion happens in concrete. So in general, initially, and the first thing comes in mind, corrosion means the rust product. So what happens, first, in rebar level, the rust products are formed around the reinforcement. So those rust not right away is bad. They're forming a protective layer around the reinforcement. So generally, people think about, oh, rust means really bad. No, rusts are initially okay, with which they are forming protective layer. As you see in the picture, the black protective layers are formed around the reinforcement. But then, in the presence of moisture and oxygen, the chloride salt, as you see from the top, the chloride salt starts to, we are putting the salts on the pavement. That salt starts to ingress in the concrete, basically. After certain amount of time, as you can imagine, they start to attack the rebar. Basically, the chloride salts are coming from the top, and then they start to attack the rebar. So the rebar, the corrosion product starts to enhance. Then the problem starts. You can imagine. Initially, the corrosion products, which is basically rust, was okay, which we are seeing from anodic and cathodic products. As you see, they are forming the compounds, basically red, brown rust and black magnetite. But after certain amount of time, they get attacked by this chloride salt, basically. So once the chloride salt is attacked, so the corrosion process starts to enhance, as you see the build up corrosion products, basically. So further corrosion happens, more and more surface cracks develops, and then eventually spalling happens. Then that's where the basically the end of the service life. So when you talk about the service life of bridges or pavements, it has two part. One part we call as corrosion initiation, the other part we call as corrosion propagation. So corrosion initiation is from the beginning of the basically construction. Once the concrete hardened, the construction is finished, to the time where the corrosion initiate, basically. So that part is corrosion initiation. And then once the active corrosion starts, until the end of the service life, we call as corrosion propagation. So total service life is equal to corrosion initiation and corrosion propagation. So that's what we are seeing. So after a certain amount of time, you can imagine that rebar can handle up to a certain level of chloride content, which is coming from the salt. So if the chloride amount exceed its handling capacity, you can imagine, then obviously the corrosion initiate. So one of them we call as chloride threshold. C sub th is the chloride threshold. Basically, that's the limit. Basically, the red line or red flag. That is the maximum amount it can be handled by the rebar. Different rebars can handle different amount of chloride threshold. Sometimes we are going to use better rebar so that it can handle better amount of chloride threshold. So originally the concrete bridges, when they are built 30 or 40 years ago, they are built with just the black rebar, black bar, we call as black bar. But nowadays we are using better quality of rebars. So not only we are improving the quality of the concrete, we are improving the quality of the rebar, both combination that can provide the better infrastructure, basically. So what kind of rebar we are using? Rebar we can use like epoxy coated rebar, the green epoxy coated rebar. Some of you probably have seen in their life. Galvanized rebar, galvanized coatings are there, and then some composite steel like MMFX. So those are the newest rebars. Generally are used by DOTs and Federal Highway Administration to better protect the rebars from the corrosion. So in that way, the threshold amount will increase. So it will again delay the initiation time. So this is the major process. So just to give you an idea how much maintenance and rehabilitation costs are done in US. So you see the total number of bridges in US approximately in 2014 level 607,380, out of which some 200,000 steel bridges, reinforced concrete bridges, 235,000, and precast concrete also, which is also a little bit of the newer bridges. Most of the bridges in California, you see the precast concrete. So they are built in the workshop panel, then the right away you can build it in the site. It's easier and it is less prone to corrosion. 108,000. So you can imagine that heavy amount of bridges, all newer bridges are built with mostly with concrete because steel bridges are so costly and the corrosion effect is huge. Even though we tell corrosion in concrete, it's kind of like a misnomer. Concrete itself doesn't corrode. It is the reinforcement, again, the steel within the concrete, it corrodes. So, being said that, we can imagine who is the most challenging part, which is the rebar, basically. So, DOT Spain, Department of Transportation, spent just 55% of their road money, 20.4 billion, on expansion and 45% of the maintenance. So, you can imagine it's like almost equal amount. 16.5 billion on the maintenance and 20.4 billion on the expansion. So you see the graph, the pie chart, how it works out. And current spending on repair and preservation, as you can imagine, how we 16.5 and we need around 45.2 billion. So which is a huge amount of our major taxpayer money is going to basically maintenance and rehabilitation. So that's a huge challenge for our concrete infrastructure. And that's why we are all the time hearing the infrastructure deal. It still needs to happen basically. Otherwise, we are in an area right now in a corner position to cope up with the technology compared to the other parts of the world even. So being said that, we need to think about what we can do. So current condition, this is the current condition. Current means not very current. Just few days ago, the newer rating came out. This is the rating. ASC, American Society of Civil Engineers, give a report card, basically a diagnostic report card, doctor's report kind of thing. So they evaluated the America's infrastructure. They gave a grade of D to pavement in 2013, and lowest grade is basically your C plus. So in 2020, the new report came out, just 2021 actually, sorry, just few days ago, the new report came out, which is basically the same. Nothing has been improved. Pavement becomes probably C minus, and bridges become C. A little bit of improvement, no, not so much because infrastructure deal still didn't happen. So being said that, we can imagine where we are standing right now with our infrastructure. It's a huge challenge. We have to improve our bridges and pavements. Otherwise, it's like 25%, just to give an idea. One in four bridges in US are functionally obsolete. Again, that doesn't mean that it will fall away right away, but they're functionally kind of obsolete due to different various problems. And corrosion is one of the major challenge, as we can imagine. So now the time comes, we need to think about what kind of materials should we use, basically cementitious material. We talked about rebar, how we improve the quality of the rebar, but we need to think about how the quality of concrete we can improve, and then the different types of emerging testing. So we know in general that cement production is a very highly energy intensive process. In the big kiln, as you see, it's a 60-meter long kiln. Basically, the cement clinkers are produced at different temperature zone. How high? 1450 Fahrenheit it can go. So cement basically production itself contributes 6% of the global greenhouse gas emission. We can imagine, out of all construction, just cement production 6% of global greenhouse gas emission. It's a huge. And also on the sustainability part, as we are becoming more and more conscious about the environmental part, so we need to think about whether we need to continue with the original cement, or we can use some alternative cementatious material which is similar to cement, combining with cement and make it more sustainable and durable. So we cannot just compromise and the quality or durability of the concrete just on the basis of sustainability. So not only we're improving the sustainability, we need to improve the durability also. So that is our main agenda. So big picture, so far we talked about, we know chloride induced corrosion is the huge challenge in concrete. Every year how much money we have spent in corrosion maintenance and remediation, we can see. Then we are thinking about CO2 emission also, because cement production we need heavily. That's how the concrete infrastructure construction will go on. But that counts also 6% of the greenhouse gas emission. So when you have heavy CO2 emission, increase in the sea level happens. And when you have heavy amount of corrosion, we are verging on the collapse of some of the bridges. So if we combine together, we can see the big picture. What will be the solution? So how to reduce the CO2 emission? One of the challenge. How to save the money? We need to have economical material. You cannot use something really costly materials because already the cost is going high. And third thing, how to stop these disasters for the bridge collapse or pavement collapse. So this is the big picture. So we need to think about that alternative better materials, alternative better emerging technology testing so that faster we can evaluate our nation's infrastructure. So being said that, let's think about what material should we use. So we have to think about we should use some material which could provide increased resistance to concrete against corrosion, and it should be available throughout the US. Not only just I mean, we can use different materials from different region, but some of the locally available resources should be there. So we'll talk about how locally available resources we are using throughout the different parts of the US. Then we can think about it should be cheaper than cement or comparable, so that even though sometimes some of the materials are little costlier than cement, but overall life cycle cost will be reduced. Why? Because the corrosion initiation time will increase, it's got delayed, so that's how the overall life cycle cost will be heavily increased. And obviously, we can imagine that we are thinking about the green products, basically reducing the CO2 emissions. So sustainable, durable, cheaper. So those are all challenging part if you think about together under one umbrella. So being said that, we are going to use the different pozzolanic supplementary cementitious material. In abbreviation, we call as SCM. It is not a direct cement, but it's a supplementary cementitious material which has the properties of what cement has, and it is called as pozzolans. So let's discuss these materials. So what kind of pozzolanic material we are using? So obviously we cannot directly use 100% pozzolans for making the concrete. You have to have your original cement. How much amount? At least 50%, because cement goes through the hydration, which is very much necessary. Pozzolans also goes through hydration, but it is a little bit on the slower side because of the different chemical composition of the cement. So being said that, we are going to use some of the fly ash, which is available throughout the eastern part and the Midwest. Silica fume, a very, very fine material. We are going to talk about that each material. Then used metakaolin, some of the natural, pozzolan, and slag, which is coming from the iron industry in different replacement level. How these replacement levels have been used? This has been tested for last 30-40 years in the lab, and DOTs have recommended this amount of replacement level to better uh, combined with cement and to make binary and ternary mixtures. What is mean by binary? So cement and one component, basically one pozzolan, we call as binary, and basically we have other basically cement plus two pozzolan. When you talk about, then we are calling as ternary. So some questions came out, what is Portland cement made of? So Portland cement made of, some of the raw materials we talked about, like rocks and all the initially the limes and all these things. The raw materials feed on in the clinker, in the clean, and it comes out like a marble shaped clinker. On the other side of the clinker, for that are ground and fine material, grounded to fine material, and put in the bag, as you see the cement bag. So cement has different chemical composition. We have some calcium hydroxide, CaOH2, then silica oxide, then you have iron oxide, which provides the color, the grace part of the color of the cement. It's provided by the iron oxide. Then you have other some minor compound, magnesium oxide and other compounds. So calcium oxide, hydroxide is one of the major compounds. Then silica, aluminum, magnesium, there are other compounds are there. So it is not toxic, but better to, obviously when you deal with cement, it is better to wear mask when you deal with cement mixing. So, and these different pozzolanic materials we are going to talk about step by step. Any other questions, anything? Okay. So being said that, now moves to next one. So we see that what we are getting, these pozzolans are having heavy silica component. When they combined with calcium hydroxide and water, they provide pozzolanic reaction, and that pozzolanic reaction makes a compound we call as calcium silicate hydrate. Again, I'm not going to details of that, but that we call as CSA gel. This special CSA gel provides the hydraulic binding capacity of the concrete. So what is the outcome? It gives very high strength and resistivity. That's what we are aiming, where higher strength and resistivity. Not only the strength is going to improve, but more resistive concrete means less diffusion. Less diffusion means we are delaying the corrosion. Delaying the corrosion means we are getting the high initiation time. So that means the service life of bridges is going to be increased. That's what we want. Heavy amount of calcium silicate hydrates. It's a gel type compound. You cannot see in your naked eye, but you have to basically go through the scanning electron microscopy to see the interior of the cement matrix, to see how the CSH gel has been formed within the cement matrix. So being said that, now we are going to talk about basically the pozzolan. So what is mean by pozzolan? Pozzolan is used in conjunction with Portland cement. It is not directly used everything 100% Portland cement. So it is contributes to the properties of the hardened concrete through hydraulic or pozzolanic activity, as we talked about. So you can have different types of pozzolan we are going to talk about. You can have some natural pozzolan, basically coming from the volcanic ash. Uh, so in the west parts of the United States, especially in California, Idaho, Wyoming, Arizona, Nevada, we are heavily dependent on natural pozzolan because we have so much of active volcanoes. Thus, we are already getting the heavy amount of volcanic ash. Uh, so, being said that, we are getting some processed pozzolans also, fly ash, silica fume coming from the industry byproduct. Fly ash is coming from coal power plant, silica fume is coming from silicon industry, slag is coming from iron industry. We're going to talk about that. I think we got another questions. What about transportation by truck to the site? So that is basically the ready mix concrete company. They handle that, basically the ready mix concrete, basically already mix was done, and then they transport to the truck with some chemical admixtures have been added within the truck so that concrete should not get hardened by the time it will reach to the site. So we have the silos in the cement plant. From the silos we get this the cement in a bag, and then the concrete mixing is done in the plant, and then they are put in the ready mix concrete truck, and then they pour it in the site. Basically, that's the way it is going. So being said that, in general, the the mm, definition of pozzolan when you talk, it is a more siliceous or aluminous material which itself possesses little or no cementitious value. By itself, there is no cementitious value. But in a finely divided form, in the presence of moisture, when they chemically react with calcium hydroxide, they form a compound which is very, very similar to cementitious property. So that's the major thing. So that's why they are used in conjunction with cement, not just 100% pozzolans we can use. So let's talk about different pozzolans. So first one, we are going to talk about fly ash. So fly ash, probably you have heard about that. It is used in concrete as a supplementary cementitious material, and it is not new something. This is a mineral admixture. This was used by ancient elements like volcanic ash, similar to fly ash, uh, used in construction. So we'll see that how this fly ash can be coming. So we see that fly ash are mostly coming from the residue of the combustion of powdered coal, which is coming from the coal power plant, and they are transported by the flue gases basically. So when the residue comes, basically all the the some of the worser materials fused off, basically carbon dioxide and other materials, and then whatever is remaining, that is transported by the flue gases. And fly ash is not new again to the concrete industry. We have huge amount of coal power plant in the Midwest and some of the eastern part. So that fly ash is heavily used for last 25 to 30 years, heavily. But there are some challenges in the fly ash. Again, EPA has put some restriction, as we know that coal power plants are mostly closing down all throughout the US. So being said that, we have to find more and more alternative new pozzolans. Now, ancient Romans used volcanic gas a long, long time ago as a natural pozzolan in construction. So, how the some of the pictures you see, one of the really great picture. This is Appian Way, gateway to Greece from Rome. It was built in 312 to 244 BC. 410 miles long, a pavement built with just volcanic ash. That time technology was not there for your quality control of the concrete, but it's just the volcanic ash, and these roads are still standing with some minimal problem, but still standing. So these are the great, the part of the concrete, innovation that we can talk about. Will the use of these additives increase the compressive strength of the mix? Yes, definitely. So when you add fly ash, slag, silica fume, and other material with cement, when you make the concrete, definitely the compressive strength of the concrete will be heavily in the long term, not in short term. We are already talking about that long term strength and durability. That's the thing we need to think about. So this is one of the wonders that we can think about. Another picture, let's show you. This is one of the biggest Pantheon. It was built 118 to 135 AD, concrete dome structures without any rebar, 143 feet in diameter, one of the largest concrete dome in the world without having any reinforcement. So they are still standing. These days, you cannot build a concrete structure without reinforcement. Why? Because we know concrete is very weak in tension, just we talked about. So that's why we put the reinforcement. Reinforcement takes care of the tensile capacity of the concrete. Whatever the weak part of the concrete, that is covered by the basically reinforcement. So this dome didn't have any reinforcement and they are still standing. So these are the wonders how these are happening. So researchers going on without having any reinforcement, how these pantheons are still standing. So we see that this is not a totally new material, but the technology, standardization, how we use in conjunction in cement, maintaining the quality control, and we are talking about the sustainability. That is the today's era that we are dealing with the concrete. So let's think about when you talk about fly ash. We have two types of fly ash are there. One of the fly ash we call as class F, which is basically having low calcium, and it is coming from bituminous coal, and it is more like pozzolanic. And the other one we call as class C fly ash. It is burning of the subbituminous or lignite coal. Different types of coals are there, and it is more cementatious and pozzolanic. So we know that cement has cementatious properties, and pozzolans have their pozzolanic properties. So we are using different types of pozzolans, but they are not the same. Even within same pozzolan, class C and class F. Class F having low calcium. We know cement has more calcium products. So when class C having more calcium product, so they are becoming more and more towards cementatious and less pozzolanic. Whereas class F having less calcium or low calcium, so they are more pozzolanic than more cementatious. So just different levels of chemical compositions are going on, and accordingly we'll use the replacement level wherever we want more. So these are the scanning electron microscopy picture of the class C and class F. You see both types of fly ashes are spherical in nature. Cement particles are also spherical in nature, but the advantage is here that they are smaller than cement particles. So when you are using with cement particles, they try to fill up the voids. When it have more and less voids, basically when you start to fill up the more voids, then obviously again chloride a hard time to diffuse through the concrete, as you can imagine. So more void, easy path of ingress. Less voids, obviously it's becoming more impermeable. So when it become more impermeable, basically less diffusion, and less diffusion means we are getting higher initiation times. So how much smaller than cement particles? Cement particles are around 50 to 100 micrometer. These are around 25 to 50 micrometers. It is smaller than cement particles, but not too small. But at the same time, they are filling up the voids. And due to the smooth spherical nature of the particle, when you combined with cement, they're easy to deal with, like compaction and rolling within the pavement and bridges, it becomes easier basically. And it has obviously you know less water demand, so it is easy to deal with fly ash basically. So this is the some of the unique properties of the fly ash we can imagine. So let's see the next one. So when you see, just to show you the picture, so left side picture is the cement particle picture. So you can imagine cement particle has a bigger particle size compared to the fly ash picture. That's one of the things just I need to mention. So fly ash, when you used in combination with cement, it is cement replacement is done by mass. So you can happen like we are using 80% cement and 20% fly ash. It could be class C or class A. So it is used as a supplementary cementing material, as we talked about, SCM, and also it is used as an admixture. So the name sometimes it is called as pozzolan, sometimes it is called as supplementary cementitious material, and sometimes it is called as mineral admixture. We have two types of admixture: chemical admixture and mineral admixture. So this one is called as mineral admixture. So it is an integral material in concrete, as you can imagine, and cost is also related to transportation part. So we can imagine that in west coast we are becoming we are relying on fly ash, but at the same time we are more relying on volcanic ash because we have the so much of resources basically. It's all the ash mines are there, volcanic ash mines throughout the Idaho, and we have used in our lab. I got the donation from some of the companies, those natural pozzolan. But fly ash, if we need to use, either we need to get it from Wyoming or we need to get it from Midwest or East Coast. So being said that, even though it is a sustainable material, but if you start to heavily bring it from the East Coast or Midwest, then the transportation cost will increase. At the same time, that will contribute also CO2 emission. So we do not want to go back to the original condition. Yes, we can rely, but we need to use the locally available resources. So every region uses their more advantageous material. That's why it is heavily used in the Midwest and in the eastern part, and the even in the southern region. But in West Coast, it is used in a moderate way. So heavy benefits are there, as you can imagine. So what are the benefits? It provides long-term strength, as we talked about. Short-term strength could be a little bit, lower than even cement, original concrete, but long-term strength will be really high, and it provides resistance to everything, like sulfate resistance, ASR, less heat generation, less water demand, and it needs less chemical admixture, pore refinement we talked about. It fills up the void, so that's big advantage, and it can consumes the calcium hydroxide. So those are the heavy advantage. It's becoming impermeable concrete, easy to deal with concrete, and provides protection, not only corrosion, it's sulfate resistant, yes, everywhere. And then what are the challenging part to deal with fly ash? As I mentioned, initially short-term strain could be low. So we do not need to get scared that the short-term strain is a little bit lower than concrete. But in the long term, we are talking about long-term durability and strength. So that is really good. Then what are the other challenge? Sometimes some of the fly ash having high calcium. So when you have too much high calcium, especially class C, then the challenge is the purpose. We are using pozzolans, but if you start to have really high calcium, that towards going more cement. So it is going too much more cement, it's becoming almost like a cement, not too much benefit. We have to use heavy level of replacement. That's one of the challenges, some of the fly ash, especially class C. And what are other challenges? Sometimes we are having initial time of setting gets really longer. So specifically when you are hauling the concrete, that's also another level of challenge. And sometimes some stresses of high carbon has been found. Even though, carbon is fused up to as a carbon dioxide in the atmosphere during the from the coal power plant, but there is still sometimes high traces of carbon has been found in the fly ash, which is the challenging part basically. But with all these advantages, disadvantages are only very minimal basically we can think about. Now we are going to talk about slag, another sustainable material, where it is coming from the steel industry. Slag, it's a granular form. Rapid cooling happens for the slag. How it is formed? When the molten iron basically in the blast furnace, slag is rapidly chilled, immersing in water. Then we are going to get the blast furnace slag. And it has three different categories. I mean, three grades we are talking about: grade 80, 100, and 120. So, you know, different grades, different activity level. Obviously, 120 is more active slag, 100 is the moderate, 80 is the minimal active slag. And its cost is related to, again, transportation and grinding, how much finer material we are getting. So slag is kind of also towards more cementatious time. It's your particle size is smaller than cement, but not too much. So it is also used as a cement replacement, and it is heavily available in the Midwest and in the South and East Coast. Slag is very, very rare in the Southern California and Northern California, because we do not have any slag silos around here. So mostly ready mix concrete company avoid slag in California. Again, it is very popular, as I told, in the some of the region, but not in the basically West Coast, because of the not availability in the locally available materials. But it has heavy advantage. What are the advantage? Let's see that. So slag is looks like a more whitish gray. As you see, different pozzolans have their different colors. As you see, fly ash is more, more whitish, and this one is gray and white, little bit combinations colors are there. So now see what are the benefit. Benefits are similar as we talked about. Major benefits: it provides corrosion resistance, sulfate resistance, ASR resistance, poor refinement happening, again, filling up the voids, less water demand, easy to deal with, providing long term strength, and less heat generation. As it provides less heat generation, they are sometimes also heavily used in mass concrete structure. Mass concrete means dams. Dams goes through, really, as you can imagine, thermal cracking. Why? Because interior portion of the dam, the walls are so thick, interior portions are, as you can imagine, are cold, whereas outside could be very hot because of the sun and the environmental conditions. So being said that, the difference of temperature can create thermal cracking. So if you make the dam with some material which is generating heavy heat, then obviously the thermal cracking would be imminent right away after a few years of construction. So that's why in the dam, in a mass concreting on a heavy foundation, large foundation, we are these days heavily using slag, basically combined with cement. The reason is it provides less heat generation. When it generates less heat, that means the chance of thermal cracking will be very, very less. Again, we cannot remove the whole thing, but just trying to make a better concrete. So what are the cautions? As slag is more like cementatious, so you need heavy amount of replacement. Less than 20% or less than 30% of cement replacement will not provide any benefit. Rather, it could create more disadvantage. And we have to think about, we have to use some chemical admixture to control the strength. Short-term strength is low. As we talked about, some of the materials provide low short-term strength, but long-term strength is better. And time of setting is also challenging. Sometimes it takes long time basically for setting, so which is challenging in the winter region unless you use a good amount of chemical admixture to accelerate the process. Basically in hot region it is another, is easier, but in a winter region it is a problematic sign, as you can imagine, for ready mix concrete trucks. So now let's move to other material. This is another material we call as silica fume. Where it is coming? It is the byproduct of the silicon and ferrosilicon alloys. Big difference between now your slag and fly ash with silica fume. We are going to talk about that. Uh, so we see that microsilica. It's a microsilica. How fine this material? This material is 100 times finer than cement particle. So you see the cement particle, how big it is compared to silica film, how small they are. So how small? Just to give you an idea, silica fume surface area is 20,000 meters square per kilogram, whereas tobacco smoke surface area is 10,000 meters square per kilogram. So now you can imagine how fine this silica fume material it is. So it is sometimes sold in liquid form, sometimes it is sold as in powder form. Both ways they are attractive, but you just need a little bit of that. You do not need too much. As you can imagine, just 3 to 10% of the replacement will make it really, really dense concrete because of the fineness of the material, and it is blackish in color. So if you want to build architectural concrete, probably it is not a good choice. But if you need to make really good impermeable concrete, then silica film is one of the ultimate choice. Basically highly impermeable concrete, so very good for basically corrosion resistance and other durability problems in concrete. So I think I got another remark. So building dams require cooling pipes. Yes, that is true because of the the heat generation. Because when you make the concrete again, this dams and heavy foundation, and that's where you need to have the cooling pipes to reduce the temperature of the concrete. Because once the concrete temperature goes above 150 degree Fahrenheit, then the whole concrete composition starts to break. This will be a major challenge for thermal cracking. So not only we are using less heat generated materials, at the same time externally we need some of the mechanism to reduce uh, the thermal cracking part. That's why cooling pipes are very important in big foundation and dams. That's true. So being said that, now we move to other part. So when you talk about the silica fume, it is a residue from the ferrosilicon products, and extremely fine amorphous materials, as we have imagined, usually used in granular form, but sometimes it is used in also liquid form. So it is very costly compared to cement particles. The other two materials we have seen, uh, basically just a ballpark game, cement price $100 per ton, whereas fly ash is $60 to $70 per ton. Similarly, steel is $70 to $80 per ton, whereas silica film is way higher, $300 to $400 per ton. So even though it is very costly, that's why we need very little bit of the replacement. The reason is you do not need it. It is already so fine material, it providing the benefit without much of replacement level. So even though initial construction cost could be little bit higher, but long term life cycle cost will be way low. We can imagine that part. And cost is obviously based on supply and demand. So this is when you use silica film in concrete, then we can easily call the concrete as high performance concrete, basically. So these are the things we need to keep in mind. So what are the benefits? Heavy amount of pore refinement. This time you are going to generate the strength from the very beginning heavily. So silica film, when you replace silica film with cement, then you start to get very high strength from the beginning. Not only in the beginning, you are going to get long-term strength also. So that is the biggest advantage of the silica film compared to fly ash and slag. Fly ash and slag provides a little bit low strength initially, then they catches some and exceeds the original cement strength. But silica film in the very beginning, it provides very high strength. In some of the situation, like fast track paving, the contractor mentions that I we need to pave it out in next 7 days basically, and we need to have the very good strength. So being said that, we what we do basically, that time we need to have a concrete that can generate the strength which is generally going to drain us by 28 days. So we provide silica film definitely, so that we can generate the very high strength within 7 days comparable to 28 days strength, and the fast tracking can be easily done. So let's see, we are getting some again question. So the question is, how does air entraining affect the strength of the concrete, and does it react with various additives? Very good question. So air entraining agent basically is one of the chemical admixture that provides in concrete to manipulate minuscule air void within the concrete. So why we need that? Because of the freeze thaw problem in concrete, which is not a problem in Southern California, but you can imagine many parts of the US, specifically in Midwest. And let's pick up a place, let's say Chicago. Elena, like, there in the winter we get 10 degree Fahrenheit, and in summer we get 110 degree Fahrenheit. So difference of temperature is very high due to this freezing and thawing effect. Basically, what we have, the aggregate starts to break down, and when aggregate starts to break down within the concrete, because the ice forms, because when the water turned into ice, its volume increases, it starts to expand, it starts to create cracking within the concrete because it exceeds the tensile strength of the concrete due to the freeze-thaw problem. So when you create this minuscule air bubble within the concrete by using air entraining agent, then we are creating some pressure release chamber basically for those expansion so that they can release the pressure, so it will reduce the cracking due to freeze thaw. So that's why the beneficial effect is coming. So there are two types of voids are there in concrete. One we call as entrapped air, the other one we call as entrained air. So entrained air is beneficial because we are manipulating those minuscule air bubbles by using the chemical admixture. The other one is entrapped air, which is happened due to poor compaction during mixing. Those voids are big, and when you have those voids, that can reduce the strength of the concrete heavily. But entrained air, yes, it reduces 2 to 5% of the strength of the concrete. But when you have like a 6,000 psi or 5,000 psi concrete on 28 days, then you do not need to worry about even 2% or 5% reduction, because most of the DOTs, they expect, or their recommendation is that you have to reach 4,000 psi concrete by 28 days strength. So when it is hits 4,000 psi, all you are taking care of the durability. Strength is one component and durability is the second component. A lot of times engineers initially, like in 20 years ago, they only thought about that if we have very high strength, then the concrete will be high. Let's say my strength is 5,000 and my friend got 7,000 psi, then my friend has a better concrete. Not always. You could have 7,000 psi high strength concrete, but you could have more adverse effect in my friend's concrete because of the poor durability. So strength is one criteria, durability is the another criteria. These days durability coming into more prime spot because of the long-term problems basically. So strength up to a certain level, definitely it is necessary, 5,000 psi or 4,000 and above psi, but it doesn't matter someone is using 5,000 or 6,000 or 8,000 or 10,000 when it hits 4,000 psi concrete, especially for bridges and pavements, because they are exposed to heavy environmental condition. Whereas in buildings, if you think about buildings, then strength is more prominent because the columns needs, so strong slender columns with high strength. But bridges and pavements, durability is more challenging part. So this, obviously they react with these additives, they reduce, as I mentioned, a little bit of strength reduction happens, but the benefits is way more because of the durability part of the freeze thaw. So that is the reason we are using air entraining agent. So what are the challenge of the silica fume? We talked about all the benefits. There are some challenges of the silica fumes are there. They create a lot of plastic shrinkage. What is mean by plastic shrinkage? Silica film is a very very fine material, so it has a very very high water demand. So unless you cure it properly right after the construction of the silica fume concrete, the small crack starts to develop on the top of the concrete basically, because when concrete hardens, its volume becomes less, so then the cracks will start to develop. So that's why it's called as plastic shrinkage due to unavailability of the water. So you have to cure the silica fume concrete with proper water spraying. If the water level goes down, then obviously basically the crack will start to develop. That's why, because concrete cement needs more water for hydration reaction. Why you need the hydration reaction? Because once we have the better hydration reaction, then we have the CSI gel that we talked about initially, that calcium silicate hydrate. That gel provides the binding capacity. If that gel doesn't develop properly, then if you have more permeable concrete, then not only you are developing less strength and less durable concrete. So that's why it is a little bit of challenging because of the mechanism of dealing with silica fume concrete. But engineers know that. That's why when they deal with silica fume concrete, they know it is a little bit hard to deal with because of the high water demand. Compaction is a little bit challenging, so you have to do it faster and you have to use more chemical admixture. That's another challenge, and it is more black and gray color. But if you are using some architectural concrete, obviously silica fume concrete is not the choice, and cost will increase again due to addition of the chemical admixture. Basically you have to use some retarder in the chemical admixture form, so that it will delay the setting time. Silica fume, we are getting the other problem because fast, it starts to get set, and then starts to get hardened. So we need more time for compaction or working on the concrete, especially in Arizona. You can think about in summer, let's say in the afternoon you are dealing with silica fume concrete. There's a huge challenge basically. It moves so fast. Then we can think about how to deal with compaction and rolling back in the pavements and bridges. So that's why heavy amount of retarder we need uh, in the form of chemical admixture for better dealing with the silica fume concrete. So there, every material has their own advantage and challenges, but overall the benefit is coming into picture that we can think about. uh, what else we can think about that? It already talked the 3 to 10% mass of the cement generally we used as silica fume. 5% is very common, and it is used with high range water reducing admixture. So cost will increase, must be moist cured properly. So you see all the construction, uh, you know, with the different materials that we talked about so far. Fly ash, we talked about buildings, silica fume is very common. In the dam, as you see, we are heavily using slag, and some fast paving construction also we can use silica fume. So these are the things we can think about. There are some natural pozzolans out there where we are relying mostly in California, basically natural pozzolans. So they are heat treated and clean, and then they are ground to a fine powder. So they include, what kind of material? Clay, shell, and metakaolin, and sometimes volcanic ash also. There. So these are all whitish, mostly cementitious powder, heavily used as a natural pozzolan. So this one of the material that we have used in our lab, one of them is called as metakaolin. Where that comes, it's a special calcined clay. It is produced by low temperature calcination of high purity kaolin clay. Probably you have heard about kaolin clay. So that product is ground to an average particle size of 1 to 2 micrometer. You can imagine how fine that material also. It is similar to silica fume, way like 50 times finer than your original Portland cement. So same effect, binding better, voids are reduced, impermeable concrete. So special application we use. We cannot use metakaolin everywhere. Wherever you need very low permeability and very high strain, metakaolin is the ultimate choice. So it is used like a more additive material rather than replacement of cement. So typical addition again, 10%. You do not need heavily. It is a little bit costlier than cement also, but overall life cycle cost will be reduced, as you can imagine. Another recent materials that my students have tested very recently in last 2 years, we call as pumice. It's a volcanic ash. Where we got it donation, we got it from southeast corner of the Idaho, like 23 miles northwest of Malath city. It's a we have huge reserve of tons of millions of tons of reserve of white pure pumice that is very in high demand all over the world. You see the pictures basically. So these are naturally calcined materials, highly sustainable, zero CO2 emission, as you can imagine. When you replace pumice and other natural pozzolan, basically you are reducing the CO2 emission heavily in the concrete. So it's a environmentally low impact process, and that's why it's called ultra pozzolan. Hence, the company name is those who are producing the pumice basically. It's a lightly colored ultrafine pozzolan, average particle size in between 2 to 4 micrometer. And typically we replace cement with 15 to 25% of the pumice. So that's the new material we are testing. We are getting really remarkable results with strength and reducibility, those stuff that we talked about. So these are the things we are relying in the West Coast because it's so easily available. Pumice, metakaolin, calcium clay, calcium shell, and fly ash also, and silica fume. But not too much on the slag. Slag is rare in Southern California. So overall, now just finishing up the material part, then we talk about a little bit on the the testing part. So overall, what is the advantage of SCMs? If we summarize, most SCMs are cheaper than ordinary Portland cement. They are sustainable, no CO2 emissions. They are way stronger than ordinary concrete when mixed with OPC. They are durable against corrosion and other potential problems in concrete. What else? They are also easy to use if you know the properties. Definitely, silica film has challenges, some of the challenges, but once you know the properties, you can use better chemical admixture to deal with those type of materials, basically. So this is the overall benefits of the sustainable and durable materials, which are now heavily used these days in the concrete bridge decks and pavements all throughout the US. So nowadays, no new bridge decks are just built with ordinary Portland cement concrete. You have to have some binary and ternary mixture. Binary means again cement with one pozzolana, ternary means cement with two other pozzolans, basically. And the replacement level we talked about. Now I'm going to talk about a little bit on the testing part. So one part, as I mentioned, my one part of presentation is the materials. The second part is basically what kind of testing should we do, new testing technology, so that we can better predict basically our concrete infrastructure evaluation. So one of the thing you can imagine, originally they were tested by the strength testing which we have in our lab, civil engineering lab, and we can check for our compressive strength for universal testing machine, basically. Again, I'm not going into details of that, but we can think about, we can provide better. These are destructive testing. We can plot the graphs, we can get the stress versus strain, and we can get the strength easy ways. We can test it 7 day, 14 day, 28 days. But the question is, this destructive testing needs heavy amount of manpower, lots of materials, because we are crushing, so we need heavy amount of materials. We need representative at least 3 to 4 samples, and we can may crush it and get the strength and modulus of elasticity. But question comes, are these destructive testings are good enough to protect the condition of concrete after 10 to 15 years of due to corrosion and durability problems? Or should we come up with some new emerging technique so that we can predict the corrosion and strength? So one of the thing we can think about, we just checked how the strength has been measured in a destructive way by crushing the concrete. There is another way we can check the strength indirectly by measuring temperature and time by maturity meter. These are all non-destructive testing. This maturity equipment you can just put in log in the actual bridge deck site. Automatically it records right after the you basically the concrete pouring, you put it back with the sensors and it measures the time and temperature. That indirect way provides you the strength of the concrete. So in that way you do not need to destroy the sample, basically. You don't need to test that many samples. You just provide some maturity meter, different locations of the the concrete bridges right after the pouring. Yes, and that way you can find the maturity, which is basically maturity of strength. We are getting indirect way maturity of each of the high performance concrete mixture. So that is very very advantageous. Why? First of all, less manpower. You are not, this automatically records the data within the machine and then you can download in your computer, basically. It saves the money, as you can imagine. uh, and then obviously it is reliable equipment, very precise data it can provide over the long period of time, as you can imagine. So this is one of the major thing we are checking for the strength. Then for durability, we are having several pictures, as you are seeing, several non-destructive testing. This is the technology right now. US is gaining heavy on momentum using different types of non-destructive testing to evaluate the concrete infrastructure. One of them we call as all basically based on artificial intelligence and based on sensor based technology. So one of them measures the resistivity. You see the different resistivity techniques, surface resistivity meters, Wenner probe, 4 points Wenner probe. You just touch the meter on the concrete sample. You are not destroying, you are just touching it with the water, basically sponges, and it gives the resistivity value right away. That resistivity value we talked about. So if you have high resistivity value, we have less diffusion right away. Similarly, we have some conductivity measure basically in the concrete. Again, the sample you plug in within the ends of the Marlin meter or Archon, and then you record the conductivity of concrete. So conductivity of concrete is another indirect way measurement of evaluation of infrastructure. Why? Because we are comparing like a charge from the physics we know. So if more charge passed through the concrete, so this is an indirect indication that more chloride can diffuses through the concrete. So we are just comparison. We are trying to simulate the corrosion condition of real life within the lab by charge pass mechanism. So more and more charge pass, enable concrete. So we need to make concrete less charge pass, less conductivity basically. High conductivity means more charge pass. More charge pass means more corrosion, more diffusion. So when you are testing different high performance concrete with this equipment, we are trying to get the idea that less charge pass, less conductivity, high resistivity. And if we are facing those type of things with this new technology, these are becoming so attractive. They are providing very precise data. They are providing, fast, easy to use. You can save money, and readings are taken like, in 5 to 10 minutes. So all the way it is advantageous. They are costly. You can imagine how much cost. Not too much. I would say each of the equipment that we have in our lab, like $3,000 to $5,000 each of the equipment. But you can imagine if you can save that a high amount of money even overall in the cost. So that this amount of initial non-destructive testing is not that much. And it can, we have equipment for moisture measurement in the concrete, as you see in the left side of the picture, moisture measurement, because we know concrete, due to change of moisture level, it can changes all the values. So these are the newest techniques, basically Marlin meter, Archon tester, Wenner probe, everything measures the durability part, as we can imagine. And testing time less than 3 minutes per sample. You can imagine when you do the like destructive testing and big corrosion testing, you have to measure the concentration of the chlorides in the cathode and the anode sample, which I can show you. Like, this is the Wenner probe technique. This is so easy, just touching 4 probes on the sample, 4x18 cylinder, turn the detector on, place the probe, these 4 probes, 1, 2, 3, 4, and take the readings at quarter points, because concrete has quarter point, 90 degree, 180, 270, 360. So then you get the your resistivity in kilo ohm centimeter. Overall testing times is less than 1 hour. Thinking about preparation time and everything together, nothing. If you do big corrosion testing, that can take hours and hours and days, which is very, very disadvantageous. Compared to that, how much beneficial are those, you can imagine. So this is the measurement technique. Again, I'm not going into details of the 4 corners you are measuring, 1, 2, 3, 4 basically. So you get data points. This is then basically equipment. These equipments are heavily Recipot Prosig. It was originally developed in Germany, but now US has their franchise. So we get the equipment from the one of the US branches, and it's so small. It's just very small equipment, nothing basically. It's 1 feet long, the length, and 4 probes are there. So it's so easy to use. Even high school students can use it basically. But it can provide the data that is so much reliable, as you can imagine. Do SCMs provide advantage when uh, I'm just seeing the question still not fully there. So when you are using this equipment with different high performance concrete, when you are using the SCM, as we talked about, they provide very high resistivity. So we are using better material. We are evaluating the basically concrete with better equipment basically. So that gives one of the better advantage, as we talked about. So SCMs provide better advantage when the earthquake occurs. Question. So yes, some of the materials SCM provides better strength. As we talked about in the building, the strength makes a big difference in the earthquake time. So that time it provides really, really high strength, specifically silica fume concrete. So that can provide up to 10,000 psi concrete on 28 days. That's the strength we use in concrete the design of the buildings. So definitely it provides high strength and durability both ways basically. So now we see that how the testing parameters are done. Again, I'm not going into details of the how testings are done, and we are just interpreting with the charge pass. Remember, the charge pass is the indirect indication of the corrosion propensity. So if you have high charge pass from any concrete like 4,000 coulombs, then it's a really bad concrete. So original concrete, those who are just using ordinary Portland cement, they generally goes through like 3,000 to 4,000 coulomb, which is really bad. High chloride ion permeability because charge pass is so high. So they are correlated with surface resistivity. So 4,000 more than coulomb charge, less than 12 coulomb centimeter of surface resistivity. They are equivalent. So indirect way, we are correlating surface resistivity with the charge pass. So our aim to go very low charge pass, which is basically 100 to 1000 coulombs of charge, and resistivity 37 to 254, which we got with different materials that we talked about. We got sometimes surface resistivity values are really high on the long term, 28 and 56 days. So these are the advantages we are talking about. The newest measurement technique with newest material, we are getting very low chloride ion permeability. Very low chloride ion permeability means very less diffusion. Again, we are coming back to the original talking point. Basically, we have to get less diffusion, big initiation time. So there are these are the some results. Again, if you see, these are the mixture that we have used. First one is the original mixture, 100% type 1 Portland cement. Then just to compare one of the better quality mixture, let's say this is the better quality mixture, 65% cement, 35% slag, G120S. How big the resistivity values? Only just on 28 days, 28 kilo centimeter. So that gives an idea. Most of the binary, these are binary and ternary mixture basically. So either two component and three component. First one is the only 100% Portland cement. So you can imagine that most of the binary and ternary mixture provide the benefit compared to your 100% Portland cement mixture. So these are the initial data. We have tested more data later, but I just wanted to show some initial data. So that is the beneficial effect. We used better materials, sustainable, durable. We tested with the better non-destructive emerging techniques, and we got the result value right away. So you do not need to rely for long-term testing. And then we get also charge pass data. Again, you see charge pass to decrease. The values have started to decrease. The first one is the original control, means 100% Portland 7. Now you see the graph starts to reduce. Most of the binary and ternary mixes showing so less charge pass. How low? You see some of them. We talked about 100 to 1000. That's our aim in between. So all of the binary, almost binary mixes got very less charge passed. Is there a database of the kind of concrete that compose major structures? Uh, compose well, kind of concrete that compose major structures in the country? No, there is no database. It is just go by structure based on the purpose of the project, and based on the, you can see some of the DOT website and federal highway website, so you can get individual but not combining together, because concrete is used in buildings, in bridges, pavements, dams and tunnels. So each individual infrastructure are dealt with individual way. So there is no big database that we can get for everything together. Uh, Under separate database for bridges, you can get everything together, federal higher administration, but for buildings, you have different part, or tunnels and dams. So being said that, we just have seen how pumice-based mixtures are performing at 56 days charge pass. So there is a huge improvement from 2000 coulomb charge to almost like 150 coulomb charge when you start to use the heavy amount of pumice mixture, which we are relying on West Coast, as you can imagine. So you would think that this would allow prediction of the future failures. Yes, it is, prediction is based on modeling, based on the results, but we need to think about the periodic monitoring part that I'm going to talk a little bit right after this slide. So you see that you can avoid the failure. Just you talked about the failure, because periodic monitoring is one of the major thing. Once it's built the bridges, go back every year, some basic maintenance, which is very less, but then every 5 years you need to evaluate the concrete bridges. I'm going to show that so that you can predict the failure when the major rehabilitation needs. So let's show you the part. uh, this is the old testing, basically old corrosion testing, hours and sometimes days versus 3-minute testing. Just wanted to show you the conductivity. So this gives the idea which direction we are moving in the testing part. So, and we talked about the service life. Basically we have two parts. One is your initiation, the other one is propagation, and we use different methodology get to diffusion from the charge passed. Basically aim is diffusion. We applied the charge passed, we get the diffusion, we put it back in our equation to get our initiation time, and then you get the propagation time to get the total service life. As we talked about, initiation is the time from the construction to the red flag, basically when the corrosion initiate, right after. And then from active corrosion to the end of the service life, which we call as propagation. So total service life is the initiation plus propagation period. So again, I'm not dealing with all the different models right now. Later, I'll just talk about what we did. The case, one of the case studies we did few years ago during my PhD time in Pennsylvania. Case studies of I-99 HPC bridge decks. So these bridge decks were built on I-99 freeway, as you see, Bald Eagle County. So 10 bridge decks were built in the I-99. The the orange freeway sign, as you see, 10 bridge, high performance concrete. So that was kind of like a ternary mixtures were used, heavy amount of ternary mixtures, high performance concrete were used. And then these concrete mixtures basically were in that's the history. Basically in October 2000, the Pennsylvania Department of Transportation started its research and development of high performance concrete for bridge decks. Currently, you can imagine how many? 4 out of the 11 districts of PennDOT, Pennsylvania DOT, are using at least some HPC concept for bridge decks. There is no way you can use original or woodland cement concrete anymore in the bridges these days. Being said that, how the monitoring was done, that's the main concept. The question was coming, how do you predict the failure in the future? So as part of the research done, as you see, 10 bridges were constructed on I-99 during 2005 and 2006. Each bridge was instrumented with temperature sensor to measure the temperature, how temperature is rising, basically, how it is affecting. Strain gauge to measure the deformation, and half cell potential measurement for corrosion potential. Everything was done basically. This instrumentation was placed within the girder or inside the deck slab and in locations surrounding the deck. So what they measured, these instruments were used to monitor short-term as well as long-term performance in the bridge deck. So on basically all sensor-based technology. So a weather station was used also to document the ambient condition, how the heavy temperature or low temperature affecting the resistivity of concrete or strength the development of the concrete basically. So construction of these decks was monitored and multiple early age deck condition surveys were also conducted. There are several evaluation strategies were there so that you can go back in after a certain amount of time to check the condition of the bridge. So are you tempted or allowed to demonstrate testing methods to your students on new construction on campus? Yes, we are basically thinking about to collaborating with facilities department, but sometimes uh, to use like new materials if it is needed somewhere, so that we can take out the old slab and we can put new slab with new materials. Definitely, that's a choice we are thinking about. We are in touch with facilities department, and if anything is needed, they told that we will reach out to you and that. Yeah, that's my plan basically. We have tested in our lab, and then definitely we can do some pilot study in our campus. Very good. So you see, we tested in this actual real life bridge deck slab. As you see, we put some eyes in the grid points to measure the resistivity. To measure the resistivity, we have the good connection, electricity connection. That's why you put the eyes, so the water makes a good connection flow of the charge. So then we measure the resistivity, actual bridge deck slab basically, with the resistivity meter. It's so easy. So it's portable. It's easy to use in the actual real bridge deck slab. We 10 years ago, basically, in the summer, in the morning time. So bridge was closed for only for 5-6 hours, and we did all the testing basically. Your moisture, humidity, resistivity, everything basically, with this sensor technology. So easy to use, as you can imagine. And as there are some of the papers were published, even as you can imagine, in January 3rd, Transportation Research Board. So our testing data. So summary, basically we are just summarizing right now. So summary of this non-destructive technique, as you can imagine, very cheap. How cheap? When we implement this technology, it saved about, one of the case study, $10 in the first project implementation in Louisiana DOT. Overall, it saved 40,000 per year. And obviously, you can imagine, public is always more aware of the cost and less tolerant about closures and repairs. So they don't want to, the bridges are closed for long-term testing. They want, their money will be purpose the taxpayers' money and we get the better result. That's how these non-destructive testing technologies are evolving all throughout the US and around the world. And we need to keep in mind this doesn't include the savings from increased service life. So we have all the way advantageous part by using your high performance concrete materials and non-destructive emerging testing technology. So being said that, the further conclusion we can draw, we are using novel use of binary and ternary concrete mixture that can easily produce very high strength, we talked about that, and high durability, saves money overall, helps to protect earth because it reduces CO2 emission. So if you replace 1% of cement with any 1% of other material, basically you are reducing 1% of CO2. That's how it is going, eco-friendly, sustainable concrete. And we are doing some health monitoring because it's like a diagnostic part. The health monitoring of reinforced concrete structure can be performed accurately and quickly by measuring electrical resistivity technique that we just talked about with the different equipments. So overall, this non-destructive testing provides so many advantage. What are the advantage if we summarize? Very simple setup. We have seen it just takes 10 minutes to set it up basically. You just sponges are soaked with water, then make the data collector on, put it on the concrete, measure the the resistivity. Very easy. Even high school student can do it. Efficient, very reliable data it can provide. We can imagine. So one of the question comes, has there been much resistance in the construction industry to these changes and improvements? Very good question. So construction industries are very much conservative on the side. So nowadays they are more started adopting this technology. So initially they are hesitant. They are thinking about, oh, how much is the reliable data? And then, with different research in the universities and other research lab, we have showed the data with some of the construction industry data, and they are now, even with Caltrans, they are now moving forward in this direction. This is the future. I mean, there is no way you can conduct an experiment for 7 days to monitor the part, the concentration for corrosion. And this is the easy way you can do. And then when you talk about them saving the money, then they are getting more attractive. They are kind of afraid of the technology. Basically, they are feeling like whether you need heavy amount of training or not. But in reality, it doesn't need that much of training, as you can imagine. So it is very efficient, easy to use, portable, as you can see, and precise and reliable data it can produce. So ready to go, directly applied, as you see the picture, in situ bridge decks and pavements. So very, very useful basically. So these are my students basically over the last 8 years use those tests that we talked about. You see the first one, the surface resistivity in our lab. We have a concrete infrastructure lab, basically our civil engineering department. So this is the surface resistivity meter students have used. Then the conductivity meter, archon tester, and then some of the obviously destructive testing they have also used to just correlate with your non-destructive data. Some of my students got really good big fellowship, David Dwight Eisenhower Fellowship. So those are really nice. To conduct the research, they got some money, intramural grant with me. They applied for the proposal. We got some money, and they have tested it for really nice material, durable material testing technology. So with that, I want to also basically acknowledge some of the companies that I got donation. I'm really thankful to them because we have limited resources. So we get donation from several cement companies, Mitsubishi. We got some aggregates from Headwaters, Lehigh Cement, BASF Chemical Admixtures, second largest construction chemical company in the world. Then Hess Pumice, we have shown the pumice in Idaho, and then Cal Portland. They always donate the cement to our lab. With that, I want to conclude my presentation. Any more question?
So the floor is open for questions, but I'd like to thank you so much, Pratnu, for a fascinating presentation. And I think we're all very proud to hear that Cal State Fullerton is conducting this cutting edge research. And to be happening here on campus is very exciting. So thank you for conducting that. Okay, so I think we're going to have to end our session here this morning. Thank you again, Dr. Ghosh, for sharing your information and taking the time to present for us. So thank you very much, and we'll let you go back to your busy day.
Thank you. Thank you. Uh,
Very good presentation. Thank you very much.
yeah,
Yay.
nice pleasure for me also. Thank you. Bye.